welcome to the new video that is related to the parity generator, that is even parity or odd parity, and then we will discuss about how we can convert from one code to another code, how we can find out the equations, how we will find out the logical diagrams, logic gates, etc. So we are starting with a problem that a 3-bit even odd parity generator. Odd parity means the number of ones should be odd, 1, 3, 5, 7, and even parity means the number of ones should be even. So we will take the 3-bit numbers starting from 000 to 111. Why we are taking from 000 to 111? Because it is a 3-bit number, so the possible combinations are 8. That is 000 to 111. And then we will find out the expressions. Expressions can be find it out using K-map, and number of K-maps is equal to number of outputs. And at last we will see how we can design the circuit diagram using logic gates. So this is the proper flow of the thing, that how we can generate the 3-bit even odd parity generator. That is, the input will remain the same, and then we will see how it will work for even parity and how it will work for the odd parity. So see what will happen over here. So it is 3-bit even odd parity generator. So we are taking 3-bit numbers starting from 000 to 111. Y is odd parity, X is even parity. So let's take a number 000. So number of ones are 0. So it means to make it a odd parity, we will add 1 from our side. And for even parity, because it is already satisfying the condition, so it is 0. Similarly, all other cases. Let's take a case of 100. In 100, the number of ones are only 1, that is odd. So if I say that okay, generate the odd parity, then the answer will be 0. Why? Because it is already odd parity. But if I want to make it an even parity, I will put 1 here. Means just like this way, that it is a P and it is your data. So data is 1, 0 and 0. So if for the odd parity, it is already number of ones are odd, so I will put 0 here. But for even parity, instead of 0, I will put 1 here. So this is the case. X here stands for the even parity and Y here stands for the odd parity. Similarly, this thing, 111. 111 is number of ones are 3. 3 means it is a odd. So if someone says, okay, generate the odd parity, it is already odd, so just put 0. For even, just put 1 from your side. So this is the case. So odd parity or even parity is, you will check out the number of ones. If it is satisfying the condition, then put 0. But if it is not satisfying the condition, then put 1. So till this point we have seen what is error, what is parity, what is Hamming code, how we can detect the error, how we can correct the error, and now we have seen that how we can generate the parity. Now we have to find out the equation and draw the logical diagram on the basis of equation. See, because it is a 3 variable inputs, so 3 variable K-map will be there. So in case of 3 variable K-map, you will put the values where ones are there, means which one are the min term. Okay, this is 0, this is 1, this is C, this is B, and this is A. Okay, always take care of this thing. If you are taking CBA, then starting with CBA. Otherwise, you can take it as ABC also, but it will be difficult while filling up the cells. Now see, if I start with the X, I am filling for X. There will be 2 K-maps, one is for X, other one is for Y. Because both are reverse of each other. So if I find out the equation for one thing, the second thing will be automatically reverse of this thing. So x, it is 0, 1, 2, 3, 4, 5, 6, 7. So it will be 1 is at 0, 0, 1. 0, 0, 1 it is 1. Then 0, 1, 0. 0, 1, 0 it is 1. Then 1, 0, 0 it is 1. And triple 1 it is 1. Okay, so the equation will be C B bar A bar, this thing, plus C bar B bar A, plus C A B, C B A or C A B, because the commutative law says A B C is equal to B A C, all are same. So this thing is C bar B A bar, C bar B A bar. So this is the equation that we are getting by taking the K-map. Otherwise also you can take a shortcut method, is just check it out where ones are there and try to make out the condition as such. Now we have to minimize this equation so that the minimum logic gates will be used, because if more logic gates will be used, it will take more wires will be used, it will be bulky, it will take more space, it will be heavy. So better thing is that it should occupy minimum space, minimum wires. So we are getting is just like C bar B bar A plus C bar B A bar plus C B bar A bar plus C B A. Okay. Now look into this equations carefully. This is C bar, this is C bar, this is C, this is C. So what I am going to do, I am taking the C bar common here, then B bar A plus B A bar okay. I am taking the C bar out of this two terms, and then you can write it down plus C, then it is B bar A bar plus BA. Now any doubt till this point? See what I did, I have just find out the equation of x using K-map, and when you are finding out the equation you are getting such thing. Okay, now what I did, I have changed the terms sequence to make it convenient that two C bar terms are with each other neighborhood and two C terms are placed in neighborhood. Now I have taken the C out common. It's up to you. You can take A common, B common. It's up to you. Because Boolean algebra, you can use any law of the Boolean algebra, as I have told you in the section of Boolean algebra also. Now understand the thing that it is B bar A plus BA bar. If you remember, A XOR B says first term into complement of second term plus first term complement into second term. So it is A XOR B. So you can write it as C bar A XOR B plus C. Now this thing A bar B bar plus AB. If you remember, it is A XOR B equal to A bar B bar plus AB. And same thing is with this equation also. So it is nothing, it is just A XOR B. So what I did, I have just write down the equivalent logic gates here, because otherwise you have to take B, then you have to take B bar, then you will take A, then put a NOT gate here, then you will take AND gate here, then put a OR gate here. But instead we can just take two wires A, B and put a exclusive OR gate and take the common term out. Now understand one more thing, that it is A XOR B complement. Just go through this thing and tell me whether I am right. See, What I did, I have just written C bar A XOR B plus C A XOR B complement, because XNOR is equal to XOR complement, or XOR equal to XNOR complement. Both are complement of each other. Now, if you can see that first term is complement of first term into second term plus first term as such complement of second term. Okay, so what is happening over here? First term complement into second term plus first term into second term complement. So first term complement into second term plus first term into second term complement is first term XOR second term. But here the first term is, that I am assuming first term, that is C, and our second term that we are assuming is A XOR B. So it is exclusive OR gate set. Now take the exclusive OR gate in between these two values. Because first XOR second, so it will be C. It will be equal to this thing. Just go through this thing. It will be C XOR B XOR A, or C XOR A XOR B, or A XOR B XOR C. All are the same thing. Means it is A XOR B XOR C. All the three inputs are exclusively OR in between each other. Now, because X is A XOR B XOR C and Y is totally the reverse of X, so you can write it as Y is equal to complement of C XOR B XOR A. You can easily see where 1 is there, 0 is there, it is 1, where 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, everywhere it is in complement of each other. So this is the equations that you are getting. Now looking into these equations, you can easily find out the logical diagrams, and then you can represent a single circuit diagram for 3-bit even odd parity generator. So this is the 3-bit even odd parity generator. So when in the parity checker, the output will be 1 when error is detected, and output of odd parity checker is 1 when the number of ones are even. It signifies the error. Means it will give you error when it is opposite the number. In odd parity, it should be number of ones should be odd. In even parity, number of ones should be even. So this is all about the 3-bit even odd parity generator. Here we are designing for X, then we have put a NOT gate here, which function is just to make a complement of the things. So complement is if we are giving X and we are getting Y. So next thing is binary to BCD code converter. Now the thing is, you are having a binary number and you want to make it a convert in BCD numbers. Binary to BCD code converter. So let us see how we can proceed it. And we know that BCD numbers are only from 0 to 9. Because we are taking the binary number and we are taking a 4-bit binary number, so we have to take all the possible combinations starting from 0 to 15. Total 16 possible combinations will be there, 0 to 15. So I have written all the values from 0, 0, 0, 0 to 1, 1, 1, 1. And one thing more, because it is 0, 0, 0, 0 to 1, 1, 1, 1, you can write the equivalent decimal values here also. Decimal equivalent values is, here it is 0, 1, 2, 3, 4, 5, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. These are the decimal equivalent values. And now what is the BCD equivalent values? We have to make out a truth table, that is input will be binary and output will be BCD. Binary inputs are nothing. It is just like 0, 0, 0, 0. Okay, 0001, 0010, 0011, 0100, 0101, 0110, 0111, 8, 9, 10, 11, 12, 13, 14 and 15. These are the binary values. But the problem is our BCD numbers are existing only till 0 to 9. Now for 10, what we will do is we will take this value is the MSB of the decimal number as such. It is 1. So we are taking a fifth bit here also because BCD numbers is only a group of 4 bits. So we have to take an extra bit to show the MSB of the decimal numbers. BCD is a binary coded decimal number where each digit of a decimal number is showing equivalent to the binary numbers. So because when I say it is 12, you will write 1 as 0001 and 2 as this way. So when I take a just MSB, because no need to take the extra bits also, I am just taking this bit. Only 5 bits are sufficient to show the conversion between binary to BCD. Okay, so I can write it as, just like if I take a case of 12, I will write 1, see, it is 1100. This is the case, 1100. Okay, then 2 is 8421. This is the case. Now come to the thing that how we are converting it. So it is 0, 0 is 0 in the binary and BCD. 1 is same as BCD. You will see that there is no problem till 0 to 9. 0 to 9 is everything going fine. But add the case in 10, 11, 12, 13, 14, 15. Now 10. 10 is, write down the first MSB as such and 0, put it 4 bits, it is 10, 0, 0, 0, 0. You can see that it is this way. Now 1, 0, 1, 1 means 11. 11 you can write it as 1 MSB as such, and here group of 4 bits you can write it as 0001. See this thing. 12 I have shown over here. 13, 1 as such. 3 can be written as 8, 4, 2, 1. 1 double 0 double 1 double 0 double 1. This is the correct thing. 14, it is 8, 1 as such. Now 8, because we have to show the 4 now. So it is 0, 8, 4, 2, 1. So it is 1, 0, 1, double 0. So it is 1, 0, 1, double 0. Last is 15. So if I say 15, 15, 1 as such. Now 5 in 4 bits will be 8, 4, 2, 1. So this is the case. So in this way there will be 4 input bits and 5 output bits. So the number of K-maps will be equal to 5. Why 5? Because number of K-maps is equal to number of outputs. So how to plot the K-map is, inputs, it is a 4 variable K-map, input remains the same 0 to 15, and for B1 find out the minterms. For B1, B0, B2, B3 and B4 just keep finding the minterms. For example, for this it is 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 13 and 15. Okay, so similarly you can find it out for other B0, B1, B2, B3, B4, and then we will put the values of minterms in the 4 variable K-map. There will be total 5 K-maps. Then we will find out the expressions, and then at last we will draw the logical diagrams. So let us see how it is happening. So these are the 5 K-maps. and we are putting the ones in the corresponding minterms. After putting the ones, now we are finding out the equations. So grouping is done that just like this way. Two quad pairs are there, this and this. By looking into left side, see, we will check at the left side also, we will check at the upper side also. Upper side nothing is in common, so I am not taking the upper portion. At the left side it is written 1 1, so it is AB. Similarly here it is a quad pair, check it left side and above, first is common, that is 1, that is A, and above first one is common, that is C, that is you have written AC. So AB plus AC is the answer for B4. Similarly for B2, B0, B3, B1, we are getting a different answers using the grouping of the Carnot map. Carnot map is used to simplify the expressions. So we are getting the simplified expressions. By this way, we are having 5 expressions with us. Now using these 5 expressions, we will draw the logical diagrams. We will take A, then we will put NOT gate, it will become A bar. Similarly for B, C, D. Okay, 4 inputs will be there. There will not be 5 inputs, 5 outputs is there. So number of K maps are 5. You can easily see 0, 1, 2, 1, 2, 3, 4, 5. Total 5 K maps are there. Next code converter is BCD to access3. Now it is a BCD number. And we know that BCD number is from 0 to 9. But when we have to use it in converter, we have to take all the 4-bit possible combinations. And 4 variable possible combinations are 16. Means 0 to 15. But BCD number is still 0 to 9 only. Now this is a problem. How we can tackle it? So write down all the possible combinations 0 to 15. Now our problem is that BCD is valid till this point. What to do with this thing? Because access3 code we can easily find it out, but when the BCD number is not existing, then what is the fun to find out the access3 code of that thing? So what we will do, for the invalid numbers, we are just writing don't cares. Because we are not sure that what will be the answer, because BCD number existence is still 0 to 9 only. Because it is a 4 variable number, we have to take the all possible combination. Now if we have to generate the output, we will just keep adding 3 in the numbers. It is 0, it will be 3, it is 1, it will be 4, it is 2, it will be 5, then 6, then 7, then 8, then 9, then 10, 11 and 12. So this is the thing. Afterwards, just keep putting the don't care. Here, 4 variable K map will be there. Why 4 variable K map will be there? Because the input combinations are 16 we are taking. 4 variable numbers we are taking. After that, the number of K maps. So the number of K maps will be 4. 1, 2, 3, 4. So this is the case. Now we will find out the equations for B0, B1, B2, B3. Okay. For these numbers you can just put don't care signs and then you will find out a expression and then draw the diagrams using logic gates. So let us see what is the expression that we are getting. So this is the Carnot map, just we are putting ones and we are putting crosses. And as I have told you earlier also that don't care responsibility is to make a bigger pair. But we are not here to make a pair of don't care only. Just like this case, we are not taking a pair of these don't cares. No need to take these don't care or these don't care or these don't care. Okay, we are here just to make the use of don't care for this bigger pair only, nothing else. So this is 4 here, 4 here, 4 plus 4, 8 means you can easily make a frame out of 8 ones, that is octa pair. Okay, now what will be the answer? above, if you see at the left side, nothing is in common, though you will not take this left side. You will see at the upwards 0, 0, 1, 0 means last 0 is common, which corresponds to D, means D bar. So D bar is the answer. So after this, next is this way. Because our motive is to cover each and every momentum, we can use the help of don't cares, but just to make a bigger group, nothing else. So otherwise only two ones are there, our group will be just something like this thing. Three terms will be there, that is a dual pair, but using this dot care we are getting a two quad pairs, that is C bar D bar plus CD, which can be further written as C XNOR D. Similarly, we can find out for this. This is the B2 and then you can find it for B3 and this is B0. There are total 4 K-maps and 4 expressions are there. After this, you can draw the diagrams on the basis of this thing. Just take a wires, put a AND gate or gate accordingly and give it a final values. Okay, this is the thing. So, the conclusion is, in this video, we have seen that how we can convert from one code to another code. It may be a binary code, it may be a BCD code, it may be a gray code, it may be access3 code. You have to take a input code at one place and output code in second place. And then you can find it out how many K maps will be there, how to find out the equations, how to draw the logical diagrams. And in this video we have seen that what is the parity checker, parity generator, what is the Hamming code, and we have seen that how to convert from binary to BCD, BCD to access3. Apart from these conversions, we can also take binary to gray, gray to binary. Just in the previous videos, I have told you the way to convert binary to gray. Okay, so now the question may arise that how to convert to binary to gray. If it is a 4-bit number, take all the combinations starting from 0000 to 1111. If it is 3-bit number, then take the combination 000 to 111. If it is a 2-bit number, starting 00 till 11. So in this way, you can find out the code conversion from one point to another point. In this video, we have also seen that what is the positional number system, what is the non-positional number system. Positional number systems was there, the weights are connected with the position, just like 8421 code was there, or we can say hexadecimal, octal, anything we can take that are a positional number system. Whereas in case of non-positional number system, where there is no concept of position. If I say no concept of position, it simply means that there is no weight is associated with the position. It is just the case that, for example, we are taking the BCD number. We are just making a group. We are just converting in the 4 bits. But we are not taking in consideration any position. Just like gray code. We are just putting the exclusive OR in between two numbers, but we are not considering the positions. Just like access3 code, we are not just adding the bits on the basis of positions. We are just adding 3 in the particular bits. So this is all about the differentiation between positional and non-positional codes. After the differentiate between these codes, we have already seen that what are the errors, what are the bugs, what are the parity bits, what is the code, what is the Hamming code, how to detect error, how to correct error, how to generate the parity, and then at last we have seen that how to convert from one code to another code. So this is all about this video. I hope we will see in the next video with some more innovative things. Thank you for watching this video.